Okay, so let's continue. So basically, last time, right, we started this new material, which basically is a continuation of lecture 4, right? But now we go in depth into using, right, the double expectation or the conditional expectation, right, and conditional variance formula, right, the total variance formula. Lecture 4, right, is meant to show you, right, what conditional distributions mean and the laws, right, and kind of convince you why they're true. Here, right, we'll use them, right, and the use, will be sort of limited, right, to just finding, right, expectation and variance, right, of a random variable. And the point is that, okay, that that you know that's not a single way, right, to find these quantities. You can always use a definition, right? But the definition calculations could be complicated, right, or tedious, or it's not obvious, right, that they will yield an answer that's simplified. Okay, so the definitions, while I guess always valid, may be computationally untrackable, something like that. While another right approach would be right for the hat problem here, where we would decompose right the random variable in question into a sum, okay, of simpler random variables and work with those simpler random variables. So that would work for like things of a counting nature, right? Find the total number of people with their right hats, find the total number of turnovers, whatever, right? But there are other random variables, right? Notably, like sort of like in the theme here, right? One of the theme, or not the only theme, of course, is first time, right, to something, right? So that's the random variable we're working on, okay? And so like I said, right, we are kind of properly in the topics, right, of stochastic process here. And what we're looking at in particular is a concept of a stopping time, right, which is a random time, right, to an event, okay, the first time that you reach an event. And so basically, right, with this structure, clearly, like the indicator function approach, kind of right is irrelevant because first time to an event is not a total sum of anything, right? It's not a total of anything. So you conceptually even is irrelevant, right? To think of it as a sum, right? So from that point of view, right, you the conditional approach is the appropriate approach, right? The conditional approach basically also is appropriate for this theme, right? To find the first time to something, because basically, like by the nature of time, you see, right? We can look at the previous event that will lead to the event of interest, right? So things like that. For example, if you want to look for the time to a first head, right, with a bunch of tails like that, right, or time to a first success, right, with a bunch of failures before that, then the event, right, that may, right, give a clue, okay, to this final event, right, of the first, success would be, right, whether the first one is either 1 or 0, right? So basically, we condition on the first trial to give us information on the, right, eventual first success, things like that, right? So conditioning, basically, conceptually, is just very natural, okay, to be applied to the framework of stopping time, right? First time to an event, okay. And so these are some technicalities that allow you to, that kind of talks about, conditional expectation, conditional variance. You can look into it, but basically, right, the example we're interested in, right, or the classical example is the expectation and variance of a geometric, okay? And the geometric, again, right, is the first time to, the success, right? And condition on the first trial, okay, which is right here, right? This is the condition, right? This is the first trial right here, okay? And so this, right, by the way, right, is the analysis of conditional distribution, right? This is a conditional distribution of x given y, okay? So basically, this slide, right, and the ones after it kind of show you basically the sequence of steps you would think through a problem like this. You would start out with analyzing the conditional. I guess you have to start out with identifying, right, the suitable one you want to condition on. That usually is the hardest step because, right, I mean, if you find the right one, then sort of by definition of right, being right, the steps below, the analysis will be easy or at least not tedious. But you find the wrong one, then the analysis below, right, will either be impossible or super annoying, right? So identify what the appropriate random variable to condition on, find the conditional distribution, and then, right, from the conditional distribution, you can work out, right, the expectation and conditional expectation and variance, right? So this is the computation, right? So basically, this is like, average out, right? The x part, okay? Because you take conditional expectation of x given y, so you average out the x effect, okay? I mean, of course, the word average here is in quote because, right, the variance is not really average, but, it has an expectation, right, aspect of it. So you just kind of, and then, right, that's the second step, right? And the third step to calculate, right, the outer variance. So this one right here, right, the outer one. So this is average out the y part, right? So there's an inner, right, expectation, which deals with the x. And there's the outer, right, operation that deals with the y, right? And again, if you get it wrong, I guess, right? So notice it hits on the y, right? X has already been taken care of. Then you will get these calculations incorrect, okay? So that's the technique. Okay. Now, so, right, and basically the example of the geometric, right, is just really a starting, right, example. The reason, of course, is that basically we're all familiar, right, with the geometric and, its expectation and its variance as a formula, right? But we don't look at it as really a first time to something. But now, once we do that, right, and we worked out the expectation and variance, then, right, it basically really is a first step, right, to, or a specific, right, or a easy example, right, or a first example to, right, this kind of set of problems where you find the time, right, to a pattern, right, first time to a pattern. So, right here, N1, right, the geometric, right, if we have a sequence, right, of IID Bernoulli, right, so which means, right, we have a sequence of 1 and zeros, right, where, each random variable, right, is independent, identically distributed, right, as a Bernoulli. Then, right, the geometric can be viewed as a time to the first success, right? The first time, right? This minimum here represents the first, right? And then I, of course, is a time variable, right? And then, of course, right? So first time to success, okay? Anyway, right? But here is basically just kind of recasting the notation, right, of the geometric into kind of a language of stopping time and let's say IID sequence, right, a stochastic process. Okay, but right, we were here, right, when we look at So now we can generalize that, or now we can kind of continue the search, right? Now, if we have the time to the first success, how about the time to first consecutive successes, right? So again, right, the language is, right, first, right, time, and, right, these are consecutive, okay? And again, right, here you have to carefully understand the context of the problem, right? This is the first time to two consecutive successes. It's not the first time to, it's not the time to the first two successes, right? Which is a negative binomial, right? It's not a negative binomial because it's not the time to the first two successes. It's a time to the first two consecutive successes, right? Anyway, and so to work on this, right? The right random variable is to condition on is the time to first success, right? And again, let's go back to the right analysis here. So it's really right that yes, right here we just tell you what the right random variable to condition on is, but what you should do is to question that sort of solution, meaning that why is it right, right? Even though, well, you can trust me that it's right, but does that mean that you cannot do it any other way, or why is it that, right, that the other approaches might not be as good or might be bad? And so the obvious thing to try, right, is say the first trial, okay, to condition on. And basically the structure of the first trial just doesn't work, right, for two consecutive successes, because you see, you really want, right, to track two, right, to know if it's two consecutive successes. So first trial kind of by structure is no good. Can you condition on the first two trials? The answer is actually, if you look at this structure carefully, you can, right? This is possible, actually, to work out the math, but tedious. All right, think carefully about it. Basically, you can find the first time, the expectation to time to first two consecutive successes, condition of first two trials. That's possible, but it's tedious. Okay, so basically, the right structure, or the ones that sort of like is, how to say this, right? The nicest one is this. And by the way, right, to be clear, and so look at the updated, right, the slides uploaded. This actually is not just conditioning on the time to a first success. Okay, it's not really just conditioning on time to a first success. I'll tell you why, right? So here the reason is we say, right, okay, you have, right, the first success, right? And you see, this is also the reason why we choose N1 to condition on, right? Because we know that by the N1 time, which is a random time, right? But by that time, we got a one, but all the ones before it is a failure. So we have a very clear structure to work with, right? We know we have a one, but before that, right, all of them are zeros. Or, let's say more intuitively, right? Let's say more naturally. You want to find two consecutive successes, right? So clearly, to get two consecutive successes, you must get a one first, right? You gotta get a first success first. So somehow you have to bypass this N1. So in that way, right, it's also more natural to think of it that way. Like to get two consecutive successes, you have to get to the first success, right? But notice that the thinking then, right, is also hanging on to the next trial after that. Okay, it'll be one with probability P. It'll be zero with probability 1 minus P. In which case we repeat, right, the search for the two consecutive ones. Okay, so in this case, this calculation right here has already conditioned on the notation is like this, xn1 plus 1. Meaning it conditions on the result of the trial after n1. Okay? It conditions on the result of the trial after n1. Because we use that information, right, in writing this out. Just like we use that information to find, right, this, right, on the we condition on the first trial. So we also condition on the trial after n1, okay, to write this down. But after that, right, everything becomes standard. So it's just really a small technical, right, writing that we want to be clear that the information we base on, right, it's not just the time to first success, but also the result of, right, the trial after that first success. Okay. But notice again, right, the structure is if you find the right random variable to condition on, then sort of you see a restart, or you see that, you know, whatever you're looking for, right, is embedded, right, in sort of the Markov property. So it will repeat itself somewhere to give you, right, of course, an equation to solve for the value. Okay. Any question about this? Okay. So then you just solve this equation, right? And we'll skip that step. But notice also, right, it is built upon the expectation of the n1, right, which we assume we'll know, right, is 1 over p. So after you get that, you get expectation of n2 to be 1 over p plus 1 over p squared. Okay, so that's the average time, right, to the first two consecutive successes. Okay. So now, just to see, right, if we understand this, if we have to find n3, right, if we have to find expectation of n3, meaning the time to first three consecutive successes, right? Right. How would we do the analysis?
We would condition on n2, right?
Correct. Okay. And right, technically speaking, we will condition on n2 and
n1, both of them?
no. And the trial after n2.
Oh, okay.
Right. I mean, again, if you miss that, it's not like the end of the world, as in like n2 is the main actor here anyway. But I want to be precise, right? I used to, as you can see, right, just say condition n1 because again, right, I drag that in, it's just kind of like more information. But if you think about it, properly speaking, you do also look at what comes after n2, right? But anyway, right, so what would that be? So notice, right, it will be n2 plus 1, correct? If, or rather like this, right? Let me show you. It will condition on this equals to 1, and like that. Do we understand? So n2, right, is a given number. Who knows what that is? But the two possible values for the trial after that is 1 or 0, right? Success or failure. So this will be n2 plus 1. Correct? And this will be n2 plus 1 plus n2 tilde, where n2 tilde is an identical copy of n2. Oh, sorry, not n2 tilde, n3 tilde, right? Because if you have a failure, right, meaning you have a 1, 1 and a 0, right, like this one right here, right? Now the dot here, of course, means it's a 0 here, right? Then the search continues, right? You understand?
Quick question. So previously, when we were trying to calculate the expectation of N2, right? When we were doing that outer averaging, we did P and then 1 minus P. Is it the same probabilities here? Yes.
Yeah, the P hits on
Yeah.
that and that, right? Yeah.
Then one
And
minus
again, right? Yeah, that's why I think this writing is okay, but it bypasses kind of some information, right? It is okay, but that's
right.
it. The P and 1 minus P exactly hits on this one and this 0.
Okay.
Sorry, 1 minus P. All right. And then, right, if you solve for it, right, etc. What do you think EN3 is?
It would be P times the expectation of N2 plus 1, and using linearity of expectation, we could say that.
Well, you could see, right, that the structure actually is exactly the same as this one, except that now you have N2, N3, N3. So you can see that it will just reduce down to P, E, and 3 is, well, 1 plus 1 over P plus 1 over P squared. So, right, so the EN3 will be 1 over P, 1 over P squared, 1 over P cubed. It will be, yeah, like that. So actually you can prove induction here for time to consecutive successes in this Bernoulli like that. Okay, any question? All right. Now, is this the end of the story, or is this the only random time we look at? No, right? The interesting thing or the crazy thing, depending on how you want to look at it, right, is the patterns, right? And the ways you can build up how you approach this pattern are innumerable, right? You can throw as a complex structure to it as you want. So let me point out, right? First of all, this structure, right, as in the IID structure of 0, 1, is the easiest structure you can come up with. Okay. So Markov chain would change that. Markov chain will make this not only taking values 0, 1, for example, also Markov chain will make this not independent. All right. So that's the structure of the sequence. But then the pattern you track, right, will also be can also be more interesting. So here we've been tracking 1, 1, 1, 1, 1, 1. Okay, boring. How about 0, 0, 1, right? Things like that. So, and of course you can just like keep on, right, throwing more and more structure on these. But for now, right, let's just change the pattern, right, and the structure will modify it, or we'll learn how to do that, right, in the Markov chain section chapter. But let's see. How do we track or find expectation to a time to telltale head pattern? Will let X be, right, the first time to telltale head in our notation 0, 0, 1, right? What do you think? How would we find expectation of X? What would the correct conditioning random variable be? Or how should we approach this problem? By the way, right, not all problems have to be conditioning. Go ahead. Anyone?
Can we use a similar structure to what we just did, where we just make an N1, 0, N2, 0, N3, 1?
Okay, but so okay, I understand what you mean, right? N1, 0 is the first time to see it, the time to see the first 0, right? and n2 0 is the first time to see 2 zeros. And I think you said n1 1, if I'm not mistaken, based on what you were saying, right? So the first time to see right, a 1. Okay. These guys are relevant somehow, of course, in this analysis. But notice you throw 3 times on the table, right? And these times don't have to all play the same role. Or, right, by the way, notice that these have some sort of structure behind them. For example, n01 always happens before n02, right? The time to the first 0 always happens before the time to first 2 consecutive zeros, for example. And then this guy probably have nothing to do with this, for example. And then we have this. So yes, these 3 times, but how do you propose we use them? Or, by the way, I'm not saying that these 3 times are all relevant. I'm just saying, sure, they sound like they have something to do with the problem. But what do we do?
I mean, my idea was less like an n11, more like an n31, where we do.
So what do we mean by n31? So I guess I don't understand the notation then, right? So I guess, so you mean like see the first 0 and then see the first 2 zeros and then see the last one. Is that what you're saying? So your notation is more along the line of like the pattern, right? Like zeros and then 1 like that.
But yeah, my definition definitely does not work. I take it back.
No, it's fine. You're thinking of how to build up a pattern. What we will be doing in Markov chain. That your thinking has that taste. But notice, right, that what you're doing, even though it's very natural in some way, is not meshing with the structure we're building right now. And that's right, the whole point of this course, that you go see different tools that is adaptable for different contexts, let's say. Okay. So what you're saying is not wrong. In fact, we will be following something like this in the Markov chain chapter. But right, what you're saying just doesn't work for, or at least doesn't fit into the structure we're dealing with here, right? Because again, notice that. Okay, let me take it back, right? What we're doing here also has that taste, meaning that, right? Let's say to find n3, right? To find n3, 1, 1, 1, we did look at, right, the first time to 1 1s, but then notice that then it's not like we jump to the last one right away, right? We look at what happens after that, right? And then condition, right? Things like that. And then to get to the 1 1, right? Of course, we look at the first one, things like that. So 1 2 1 1 2 1 1 1, right? So sure, our thinking works like that too, right? If you look at how we build up these slides, right? We start with n1, and then we work with n2, which is 1 1, and we work with n3, which is 1 1 1, right? So let's build on what you say. So you could, right? Let's say follow a similar structure, right? You would find the time to the first zeros, and then based on that, find the time to the first 2 zeros, and then find the time to 0 0 1, right? By conditioning. Does that make sense? So I think there's something to what you say, and actually we can fix it, or we can make it precise with that project. Okay. So of course, for example, right, n10 would be 1 over 1 minus p, right? n20 would be 1 over 1 minus p plus 1 over 1 minus p squared. Agreed? From similar structure to what we did. But so your project sounds okay. But one thing I want to say here in the comment is you're working too hard. There's an easier thing to do here. Is there something we can notice here? Just for this structure alone, right? Not in, so what you say works as in like apply the algorithm, right, we've done before to this new problem. Perfect, and that's a very reasonable way. Can we do something faster?
Is writing n3 equals the min for I greater than or equals to 3, x I minus 2 equals 0, xi minus 1 equals 0, xi equal 1, the same as what my classmate proposed?
Yeah, so what you're going for is just really a definition of what kind of time structure we're looking at here, right? Which is, yeah, you just kind of
Same idea, right?
not even the same idea. What you're doing is you're symbolically expressing what that time is. And then,
Right.
of course, maybe from that structure, you would do what I was saying, right? So, no, okay, it's good. It's good that you guys are trying to build up the symbols, right? Structure, things like that, which I'm not showing you here. This is something you should do for your own, right? Meaning if you want to convince someone else that this is what you're doing and convey the idea, great. It was fantastic work, but you notice right here, I'm not working with you on those things. Trust you can do it on your own. I'm working with you on the idea of the solution, meaning that, right? I acknowledge that that path is fine. It will lead to the right answer if you're careful, right, with all the steps and don't make mistake. I'm just saying that for this particular problem, okay,
I may.
there's an
Oh, wait, go ahead.
You go ahead.
No, it's okay. You spoke first.
No, my new idea was just that, like, if you do a first time to 001, you can just repeat, like, trials where it's zero, like, first success, and the first one that's length 3 would be the first TTH.
right. Okay, can you be more concrete? You're saying something there, but notice that you sort of mix certain things together. Can you be even more precise?
I'm trying.
No, I see what you're
Yeah.
getting to, but you're not expressing it in a precise language. That's all.
I know.
I have a similar idea.
Yeah.
So after you have the first telltale pattern,
Mm-hmm.
the next trial, if it's a tail, you're take the third trial and the second trial and call that your first telltale pattern. If the third trial is a head, you're a success, you got the success, you're done. So in the case where the third trial is a tail, you redo in a way such that you reset what you define as the first two tails.
No, again,
I'm not expressing
both of
it.
you guys are seeing the picture, which is great. Now, the hard thing, or still, right? This is where math requires you to take it home, right? You're seeing the right picture. I don't deny that. Both of you are describing the right picture. That sort of repeating, right? Which is exactly the crucial idea here. You're seeing the crucial idea, which makes this problem easier. That is right. Okay, whatever you do, you get once you hit on the telltale, right? It whatever happens before that. But once you hit on the first telltale, then either right you just keep repeating this, or you get ahead and you're done. Correct? That's what both of you are trying to say. Okay, but now take it home, right? What does that mean for us in terms of finding the first time to telltale head?
It's the first time to just the telltale sequence, and then
Okay.
the first time to the head sequence.
Excellent. That's it. The first time to telltale head is the first time to telltale plus the first time to head. Or rather, right, if we want to be careful, we throw a tilde in here. Because here we don't mean the first time to the head counting from 0, but counting from the first time we see a telltale. Right? You see, this right here is NTT. And this right here is NH. Correct. Do we understand? Only from the structure of the telltale head, that's why we can break it down like this. So the answer is 1 over 1 minus P, 1 over 1 minus P squared, plus 1 over P. Are we okay? So again, right, not that you have to see the structure right away, you recognize it right away. Just flavor the problems, right? Things like that. But conditioning, of course, is the right idea, is the main idea that we're selling in this lecture. But the pattern, right, could give rise to more interesting ideas than just conditioning. All right, any question? So let us talk about the last materials here. Okay, so this slide just repeat, right, the importance of sum of random variables, right? Okay, I guess I just started with, right, the beginning where I said time, right, is not about sum, but what we're dealing with now, right, or what we're looking at now is a compound random variable. Okay, this is a very important idea that happens in Poisson process as well. That basically, right now we look at a sum, okay, but the sum, right, is random in two ways. Basically, right, the terms are random, or the summand are random, but also the upper bound, right, is random. Of course, right, if you feel like it, you can also make the lower bound random. But then, right, the upper bound and lower bound are somehow connected, right? Because the upper bound must be always more than the lower bound, right? Bigger than equal to lower bound, but whatever, right? Here we just have the upper bound random. Okay, so concretely, right, you have x1 plus x2, etc., right? Plus xn, right? But you don't know how many terms there are because it depends on what n, right, comes out to be. So in terms of, right, if you look at this as a random walk, right, then this is a random walk evaluated at a random time, right? The random time that we've been talking about, right, previously, okay? So that's one way, right, to interpret the compound random variable. Another way, right, to just to give meaning to this is, let me see if I put it here, is, right, if you think about, right, let's say n is a Poisson process, right? N represents, let's say, the number of people, right, arriving at a store or at a yoga studio, okay? Then let xi, right, be the amount of money spent, or, right, let's say they spend something at the store, right? Or at a yoga studio, let's say they buy stuff at the yoga studio, whatever, right? Then notice that S here, right, exactly represents the total sum of money, right, that the store will get during that time interval, right? And when you think about that, that's a very natural thing to happen. That basically, right, that if you look at the total amount of money a store collects on a day or now, whatever, right, it clearly depends on, right, how each person spends, okay? And let's say they're all IID, okay, that's a over assumption, but that's fine, right? Let's say each person spends an IID amount, but that's not only the only issue, right? The number of people arriving into the store, right, is also random. So you sum this IID amount, right, up to a random quantity. Okay, that's what compound random variable does. And now, right, the story is that we're just kind of focusing on finding expectation and the variance, right, of the compound random variable. And hopefully, right, it's obvious that we want to condition on the upper right bound, okay? Why? Because the moment, right, you condition on the upper bound, right, then the inner expectation here, right, then this becomes just a normal sum, right? Okay, by normal, I don't mean, that is really just a sum, because inside here, the xi's are still random, right? The xi's are still random. All right, the xi's are still random, but you have taken away, right, the randomness of the upper bound by conditioning on it. Okay. And so within the inner expectation, you can, or inner condition expectation, you can operate with it just like a regular sum of IID random variable. All right, that's the key. Okay. And then, right, if you plug this in here, right, then the algebra expectation will be evaluated like this. Okay, any questions so far about this? All right, so let's point out a subtlety, right? Notice that the assumption is the n is independent of all the xi's, right? That's crucial. Meaning that, right, in the example of people spending money at the store, the amount of people coming into a store is independent, right, of the amount of individual spending at the store, right? Which sounds like actually not true, right? I mean, I guess the more expensive the store is, the less people who come in, whatever, I don't know. But let's say that they're independent, right? And that's crucial. Where do we use that assumption here? Is that assumption needed?
You're saying the expectation of xi conditioned on n is the expectation of xi, right? That step.
Exactly. That's what we use here. And notice, right? If we don't have that, then this is still correct, right? Because we are fixing n. N is known. So that's why I can pass in like this. That's fine. This is always correct. But that dropping to allow us to just calculate this as an expectation requires the independence, okay? Without independence, we can't do that, okay? So that's the subtlety. All right. And in fact, right, I mean, yeah, anyway, right? So, all right, any question here about that? All right. And so now the, yeah, right. I guess I was talking about that, right? So, right, I mean, here, right, on this slide, I just kind of give an example of what happens if the independence does not happen, right? So here, the n as I defined it, right, is basically the first time, right? The sum is 10, right? Then by definition, right, this sum is always 10, right? By definition, this sum is always 10. So therefore, it cannot be n times expectation x1, right? But of course, notice that here I construct n to be dependent on the xi's. So that's why, right? It cannot work out like that. Right. So the conditional variance, right, works out in the same way, right? But we have to use the total variance formula. And so notice, right, for this expression right here, right? So we not only use, right, the independence between xi and n to go from here to here. We will also use, right, this step right here, also use the fact that xi's are independent. Okay. If the xi's are not independent, then you cannot pass a variance inside the sum. Oh, sorry. I guess this step right here. Right. You pass a variance inside the sum because the xi is independent. And then you drop this conditioning because xi is independent of n. Is that okay? All right. So
Wait, do you mind scrolling up just for 1 second?
sure.
Okay, that's all.
Sure. All right. Yeah, right, exactly. That here I was kind of remarking, right, on the fact that variance and summation, right, does not always. So basically, I was remarking on this step right here, right? These steps I already can emphasize, right, on the previous one. Okay. Sorry, this one right here, right? Now I am emphasizing on this. So here, notice, for example, you can always interchange expectation and a sum, right? No problem, because conditional expectation is linear, right? Conditional expectation is linear. okay? But conditional variance, right? Notice here we're dealing with conditional variance. So, right, we are actually technically we're dealing with the idea of conditional independence here, which is, right, the idea that, well, unfortunately I skipped, right, in lecture 4 because, well, we don't have time, right? We want to go on to Markov chain and things like that. But if you go back and look at the materials in lecture 4, right, I elaborate on how to work with conditional independence, and how I point out that it's not the same as independence, meaning that their random variables are independent, but not conditional independent, right? Think of the yoga studio problem. I think we looked at it last time, right? The number of males and females. They're independent. They're not conditionally independent, right here. I think I repeat that example right here, right? They're independent, but they're not conditionally independent given the sum, right? But of course, because, you know, if you're given the sum, then it's identically 0, right? Because it's a constant. Do you understand? So, right, there are a lot of subtleties in working out, right, the calculation for this conditional then. Meaning that, right, of course, the whole point is, right, they're all independent. Xi is independent of n. So you have like really all the independent structures working for you. So that's easy. But the moment you throw in just a slight dependence on this, the whole calculation might go haywire. Some steps might go through, some steps may not. Okay. So I just want to kind of highlighting on, right, the potential difficulty, right, in these calculations. They're not like, okay, just pass through. Any question about any of these? Oh, by the way, right, again, the slides are uploaded, so you have the slides, but, you know, my annotation may not be there, but okay. So the final result, right, is the following. Okay. So to kind of make it a bit more simple, right? Let's say not simple, but just kind of, let's say expectation of xi, right, is mu, and variance of xi sigma squared, right? So basically, right, let's say the amount of money spent has mean mu and variance sigma squared. Then the expectation of the sum, right, is mu times expectation of n, right? So to make it easy, right? So it's the average number of amount of money spent times, right, the expectation, right, of the number of people coming in. So I would say that this result probably is intuitive or something, meaning that people would probably hit on this formula even though they know nothing about compound random variable. But notice, right, the story is not always that simple. Variance doesn't work that way, right? People might say something like variance of S is sigma squared times variance of N, but that's totally wrong, you see? It's not this term and it's not that term either. Notice, right, it'll be expectation of N times variance of X. So it's sigma squared times expectation of N. And then what? This term is expectation of X1 squared. So it's mu squared times variance of N. All right, the variance formula, even though for this simple structure, is complex, put it that way. All right, any question? All right, so I think we're sort of like 4 or 5 minutes, right, into the quiz. So for the quiz here, I would just ask you to find the, so I'll tell you first, right? So the quiz will be to find the expectation, right? For the first time to telltale head, okay? You just have to give me some explanation, right? You don't have to do the whole thing, but you can quote freely, right? What we've done before, right? But so we have 4 or 5 minutes. I just want to spend this time while I still have your attention, I guess, to say, right? So what happens on Friday, right? Which is the exam day. is that the last part of the exam, the last part of the lecture, right? Whatever, however long that is, let's say 80 minutes, right? Plus 10, right, for submission is for the exam, right? You will see that time on Lockdown browser, right? You'll see the time allotted there or on the assignment. You'll open exactly there. So that gives us like some time before, right? I don't know, like maybe 30 minutes before, something like that. That time will not be used to do lecture or anything like that. What will happen is for that time, right? I mean, maybe less, okay? I don't know. We'll see the precise time. I'll put it on the canvas. So what will happen is I will be on the lecture, right? Zoom, but no lecture. Okay, so I'll just be there for questions. If any question you have about the materials or things like that. So that time, right? You definitely don't have to be there, right? No new materials will be covered. Strong warning, right? That session is not for like fire rescue or whatever. Like, my Lockdown browser doesn't work. What can I do? I don't think anything would be done in class 30. That kind of thing, right? It's solely meant for like, okay, you have some conceptual clarifications left you want to ask, or maybe something about the structure of the exam that you want to clarify. But okay, small thing, right? Things that can be fixed within or clarified within 30 minutes or so. Okay. And that's it. It's not mandatory. People tend not to even show up, right? And that's fine. If you don't show up here, right, you just kind of join the exam, right, and do the exam on Friday. Okay. Any question about the structure of Friday lecture or any exam, right? Midterm 2 will be the same thing. Okay here. Okay, so I will turn off the sound and the video, and we will continue at 11:35. Is there any question before we continue?
In regards to the structure of this Friday's exam.
Yeah.
So the first 30 minutes, meaning from 10 a.m. to 10:30, we're gonna ask questions this Friday?
No, lectures, right? 10:30 to, because the lectures are like 2 hours-ish, right?
Oh, okay. And the exam is the last 80 minutes.
Last 90, right? Because 80 plus 10. So,
Right.
right. So I don't know, like 25 minutes, first 25 or something, right? Because basically usually the exam is the whole lecture, correct? I mean, for a regular
Right.
class. But because our summer class has more, so the first whatever remaining is too small to do anything. So question and answers are like the best way, right, to utilize that time. But no new materials, things like that.
Okay,
But
yeah.
it's still everything happens during lecture time, right? Nothing happens outside of it.
So what's the start time for the exam? 11 o'clock, say?
You will see when I do the assignment, right? You
Sure.
will see the starting time. But yeah, I mean, like, if you want to find out, right, the way I would do it is 80 plus 90 would end at 12:25, right, which is our, sorry, 80 plus 10, right, would end at 12:25, right, which is our usual end time, right? So by the time you submit or counting the submission time, that will be the end time of the class, right? So you can count that backward and see what the starting time will be. Does that make sense?
Thank you.
Yep.
Hey, Professor, I'm not able to access the exam.
Exit or access?
Yes, access.
I can't help you on that, meaning that you cannot do the lockdown browser or?
I'm done with the lockdown browser thing. But when I tried to do the other assignment, like it's just the submission thing.
Oh, right. But that's the whole point. You're not submitting on lockdown browser. There is an assignment for submission, remember? There are two assignments.
Yeah, I know, but like I'm trying to find the exam like where like the questions which we need to solve.
It's in the question, right? When you access lockdown browser, you should see the exam. Is that right, everyone else? That's how it should work, right? Once you get into the exam, you will see the exam, right? You see the questions. Any issue there? Can anyone confirm or deny that? Say again.
No, I was just saying that worked for me. Like I did see the exam in the
Yeah,
lockdown.
right. I mean, if you go into lockdown browser, the exam's supposed to show on for you right away. Yeah.
But Professor, when I did the midterm equipment check, the require respond lockdown browser, like I downloaded the webcam and all that thing, like I did the take the quiz and it comes as like download it, and I downloaded it. But what's the next thing? Like it's not showing the exam.
So that is something I don't have like, let's say, knowledge on. You can reach out to Canvas or lockdown browser team to see what. So you have to register for lockdown browser or something along that line. That's the first thing. You have to install it, and yeah, I only know that if you do all the steps, you will access the exam, right? And this is exactly why we have equipment check, so that right, you detect all these things and then have time to solve it. That's all I can say, right? But yeah, I mean, it always worked, or it works, right? I mean, people have done it, people are doing it right now. So it's not straightforward. Okay, you have to do something, and if you have issues, again, unfortunately, my technical knowledge is not on that part.
Like for the exam, like it's on the assignment that you posted, like require respondents lockdown browser.
Correct. Yep. So
But
if you have,
like when I go there, it's showing that as like take the quiz, and when I do the take the quiz, like it's coming as like you need to download it, but I already downloaded it.
did you install it? Did you do whatever
Yeah,
you need to do?
I did. I installed it.
Okay, then if I'm not sure you're in another country or something like that with VPN on or whatnot, but like I said, I mean, not that I'm not trying to help you out here. I just have no knowledge on that. Right? I never was on that side of thing where I took the exam myself. I just set up the exam as I'm supposed to, right? And so reach out for Canvas help or reach out for responders help. I think they're like, right, they have some sort of like help team 24/7 or something like that. Yeah, right. Again, unfortunately, that's online classes for you. You have to have it. All right, that's all I can say. Okay, I'm not trying to like shirk off my responsibility here. I have no idea what happens on that side. I just know that it's possible, but fixing things, yeah, not what I do. Okay, so but try to do it. All I can tell you is like that's required for the exam.
Hi,
Okay.
Professor.
Yeah. Yep.
I just failed to submit my quiz. I don't know why. So I just emailed that to you. Is that okay?
Yeah, that's fine.
Okay. Yeah, thank you so much.
Mhm. All right. So yep. Anyone who has issue with Lockdown Browser, please resolve it ASAP. All right. We need it. You need it for Friday exam. Okay. So all right, let us take a look at the problem set. Okay. All right. So let's take a look at this one. All right. So any suggestion on how we solve this problem? You let X be the number of flips until first head. All right, how do we find expectation of X? So clearly, right? Yeah, go ahead.
Sure. So X is either, sorry, the coin you pick is equally likely, right? Like out of the 3 coins.
Sure. That's the assumption, right? Randomly pick. Yeah.
Right. So can you decompose the expectation first as a sum of the 3 possibilities? Whether you pick the first coin, the second coin, or the third coin? Because you're dealing with different independent geometric random variables.
So by decomposing, what do you mean?
So the expectation of X is 1/3 times the expectation of X if it were the first coin you chose. So that's your Y. That's what you're conditioning on.
Correct. So actually, right, to be precise, or to go with the framework, right? Yeah, Y be the coin we pick, right?
Right.
And it'll be 1, 2, 3, 1/3 each.
What
Right.
kind of distribution is this for y?
We don't have to name it, but if you want something like a discrete uniform,
Sure.
right? But right, I mean, I kind of see your motivation for that, but no need, right? Oh, you condition on something, a lot of times it has no name, but as long as we know it's a distribution, right? If we know
Yeah.
this, that's good, whatever name it is, right? I mean, the recognition of the name comes in when we want to use this knowledge for, like, let's say, expectation and variance, right? But this is simple enough that we probably won't need. So, for example, right now we have expectation of y, x, y equals to 1, right? Would be 1/1/4, let's say, right? And then so x, y equals to 2.
That would be 2 and then 4/3.
Yeah, correct. Right. So that's the formalization of all that. And then, sorry, 3/4. Right. And now, so expectation of x is expectation of x equals y, right, which is going to be 1/3 times blah blah, right? Sum of all these. All right. Any question?
Wait, so so find the expectation, we have to basically sum those three probabilities, 1/1/4, 1/1/2, and 1/3/4, and then take 1/3 of that?
Well, so I was being lazy here, right? It's really 1/3 times this plus 1/3 times this plus 1/3 times this.
Oh yeah, that's what I was saying. Okay.
Which is 1/3 times the sum. All right. So B would be the same way, right? Condition exactly the same random variable. And right, and find it, of course, with the different answers here.
The difference would be that in previously, right, in part A, x conditioned on y follows a geometric distribution, but in part B, x conditioned on y follows a binomial distribution with any.
Excellent, exactly. 8 and 1, whatever, right? These
Right.
things. Excellent. Yeah, what you said is exactly. Okay. Let's skip this one. Wait, hold on. Yeah. Okay, let's look at this one. All right. So notice this is yet again, right? Another one of those first time to something, right? But the event that we're looking for here, right? So it's really first time to an event, right? A pattern can be a way to say, but first time to an event, right? An event here is not, so the pattern here is not, right? I mean, a fixed pattern, but 2 of the most recent 3, right, are heads. Okay, so how will we deal with this?
Could you condition? I mean, are there only 2 ways that you can get 2 out of 3 to be heads? You either have to have 2 in a row be heads, or do you have to have heads, tails, heads? Are those the only 2 cases?
Okay, I mean, what you say is not like wrong or anything, but how do we leverage that information? Oh, what will we do next on that, with that? So you're saying, right, either we have head next to each other, which is correct, or head, tail, head. Yep. But then how would we use this information?
You're right. I don't think that would work because you have to find the probability of each case, and I don't think that's feasible.
Well, so again, right, it's not we're if you in case, right, I mean, we're kind of away from the realm of probability, like event by event a little bit here. We're dealing with conditioning, right? So you kind of have to think in that picture. So what would be a suitable random variable to condition on to analyze this pattern? All right. Any suggestion? So I think, right, because it's 2 out of the first 2 of the most recent 3, right? That 2 out of the most recent 3, the fact that, right, they don't have the consecutive kind of rules out, right, that we want to look for 2 consecutive here, I think. So it seems like, right, either way, you have to have a head, right, to work with. So I would think that if you condition on N1, right, time to first head would be productive here. Okay. Again, right, just based on that observation. When we want to get 2 heads, well, we gotta get the first head. Consecutive 2 heads doesn't seem to be relevant, right? So, okay. So let's see here. Is this productive? If condition N1, can I say something about the behavior of N2? Of N? Because if I can, right, that means my conditioning is correct or good. If not, then we have to search for another one to condition on. What would N1, what would N condition N1 be?
That you can stop if there's a head in the next 2 flips.
No, not next 2, right? Only next one. Oh, there's a head in the next 2 flip. Okay, good. So yeah, so basically, right, you're kind of saying that we need to condition on, right, the next 2, right? Correct. So we know, right, that we got a 1 here, right? That's the first head, right? And now we want to see what happens in the next 2 slot, right? So here's the thing, right? If, let's say the next one is 1, right? Then doesn't matter what the one after it is, right? Then this will be N1 plus 1. Agree?
Yep.
All right. So obviously then we just have to look at the case when it's equal to 0, right? Then now what you said, right? If the next one is 1, right? So 1, 0, 1, then that will be n1 plus 2. Agree?
Yeah.
And then, right, if we have 2 zeros, then we will repeat ourselves. Is this okay? So these are the 3 scenarios we deal with. Right? So what would the equation be for expectation of n and n? So let's call it mu, right? Let's say expectation of n, let's call it mu, right? So what's the equation for mu? This happens with probability p, right? Agree? This happens with probability 1 minus p times p, right? And then this 1 minus p squared. Is that okay? And of course, right, E of n1 is just 1 over p, right? So we can replace that. Any question? All right, yeah. So I guess I just call it, I use a different notation there, but you know, same idea. All right. Okay. Let's try this.
Really quick, for the previous question, the wording, the most recent 3, where does that come into play?
Good question. So it comes into play in the following. So it comes into play if the first 2 flips are heads, then n equals to 2.
Oh, okay.
Right? No, I mean, not only that. Notice that the outcount is correct in that way, right? If the first 2 flips are heads, that's exactly this case here. Because that if n1 equals to 1, then that's 2. See? So first of all, right, that's used for that. The second place where it's used, right, is a bit subtle, but notice that if we condition on n2, that's wrong. So not that n2 is not productive, condition n2 is wrong. Do you see why? Do we see why?
Actually, that was my first thought. I don't know.
I mean, so okay, wrong, well, maybe it's a strong word, right? But why wrong? Why wrong is because, right, if you condition n2, that means you have a 1, 1, right? That's n2. But notice, so before that, you don't have consecutive 2s, consecutive 1s, right? But you might have this.
Oh, I see.
So that's why N2 is actually, once you reach to, right, the whole point of conditioning, by the way, right, notice we have an implicit flow of information here, right? You want to condition on something that did not lead to the event yet, right? You could condition on something that go past the event, in which case it's useless because everything now has happened in the past, how you retrieve it. N2 actually, right, has that flavor here. Not that it will always go past the event here, but it might. Right? So that's another meaning of out of the most recent three. It kind of prevents you to look at N2. N2 is actually too far. Is that okay?
Yeah, that's an important subtlety. Thank you.
Yeah. Mm-hmm. Okay. All right, let's look at this. Okay, so right, clearly the wording here has to be interpreted like carefully, right? So how would we what would the expectation be? So by the way, right, maybe let's talk about the meaning of the question, right? What scenarios are they looking for? I mean, I know the English word says that, but is that clear to us? Give me an example of the scenario in the question.
I mean, I guess the base case is head, tail, or tail, head, then you stop right there. N equals to the number of flips. For the first question, which asks for the expected number of flips that lands on head, because it's a counting variable, I want to think X follows a binomial distribution, but N
Sorry,
very
no, the first question is here. I think the format's a bit weird. It's here
Oh,
first.
sorry. Okay.
Find the total number and then, right? Yeah. So what scenarios are we looking at?
The first flip gives you either a hail or a tad. I mean, a tail or a head.
Yeah, tail,
So
head or
then,
tail. So what?
yeah, once you get that head, you're just looking for the first tail, and then once you get the tail, you're just looking for the first head.
Perfect. Excellent. That's perfect. So right, actually the subtlety here or the confusion, if any, right? If you look at like the first head or first tail, right? Whatever that is, right? Notice that, let's say normally if suppose you have something like this, right? That's a usual scenario, first tail. Then right, you kind of have the head tail built in, right? But notice these are not the same time, right? So what are they? So it turns out that, right, it's not the time to first head, the time to first tail is what we're looking for, right? But we should exactly condition on, so let's call it n, okay? The result of the first toss, right? The first toss is a tail, or the first toss is a head, right? Exactly, and then perfect, right? As we say, if the first toss is a tail, so maybe let's make it that way so it's clearer. Then, right, it will be 1, right? Because you already have a tail here. And you will look for the time to the first head. But if the first toss is a head, there'll be a 1 and a time to a first tail. Are we clear on this?
Yeah, that's fairly intuitive.
All right, so the answer then will be, right, expectation of n is 1 minus p, right, for tail, and then 1 plus 1 over p, and then p 1 plus 1 over 1 minus p, right? We can say it directly like that because all these numbers are easy to know, right? Good. All right. Let's now look at B and C then.
We talked about sums where the upper bound is random. Is this an appropriate use of that?
No, I don't think it's.
Okay.
Why would you think about sum here?
Because you're finding the number of flips, so it's a counting variable. I don't know.
No, again, right? I think I said about that at the beginning. This has a flavor of time rather than
Okay.
the total, right? I mean, okay, it's a discrete, so somehow it could always be cast as a sum. But we think about it, again, just my seeing this, and I can see the random time nature there. But if you carefully unpeel, right, that structure you're suggesting, then the upper bound seems like the time you're looking for. So you're kind of circular, right? Go in a circle. You put what you're looking for as a complicated structure inside the sum. So it's already there. You're not making it simpler, you're making it harder. Right. So no.
That makes sense. Okay.
And again, right, clearly part B somehow is related to part A, correct? Because the number of heads somehow should be related to the total number of flips, right? Because it's a tail and a head. So I don't know. Sounds to me like, again, I'm not trying to say you can get the answer directly from A, but somehow the way of thinking of A, right, should be, isn't it, relevant to the way of thinking of B and C, right? For example, what's the number of heads needed condition on the first toss? Sorry, the number of heads in the flip, right? If the first toss is tail, then the number of heads will be
Just 1.
correct, right? There you go. So you can redo the same analysis, right? So let's just do, right? Let's call it N, whatever, right? Let's call it NA, right? The answer to A, right? So NB, right? If the first toss is a tail, will be 1, right? And B, if the first toss is a head, will be
tilde NT.
excellent, right? Because exactly, right? It's the number of toss until you get to the first tail, but you also have the 1 here. So technically speaking, right, it's 1 plus this minus 1, right? 1 plus this because it's a total number of thing. Subtract 1 because the last one is the tail, if you want to look at it that way. Okay. So the answer is 1 minus p, right? Plus 1 over p times 1 over 1 minus p. Okay. Any question about part B? All right, so let's skip part C, okay? So this is similar. Let's look at part D. And D only asks you to repeat part A. Again, right, what should we condition on?
Maybe bad idea, honestly, but like, what about the random variable used in part A, like the n from A? So condition on the first time.
No, it sounds like an
Oh.
excellent idea. It sounds like an excellent idea. I was playing around with the question. I was thinking condition on time to a first tail or something. And that sounds a bit awkward. What you said is perfect, actually, I think. Time to the first. Let's see. I don't know, but let's see. No, it sounds good, but it sounds very promising. Let's see. So let's say ND, right? Condition on NA. Okay, what can we say about that? A total of at least 2 heads and 1 tail have been flipped. So NA, we know we have a tail and a head. Well, no, maybe not, right? That's also awkward, isn't it? Because we don't know how many, we cannot control how many heads or tails we have there. Huh, okay, no, sorry. NA sounds also awkward, right? Yeah. No, I think NA sounds awkward. Do we agree? I don't see it as kind of a nice picture going after NA because I cannot control how many heads or tails I get from NA, right? Yeah, sorry. That doesn't sound like
Oh, that makes sense. Yeah, you can't control how many heads and tails.
yeah, I mean like you can control in one case, right? One of the case you can, but the other case you can't. Right. So, you know,
Right.
so I think yeah. So I think NA is not good because you cannot control the information that you want. All right, so what should we condition on? I think, right? Actually, it can be built on A, but not literally on A. It can be built on the thinking of A. Meaning what? I propose that, right? We condition on the first 2 flips. That really all we can do. For example, right? First 2 flips can be tail tail, tail head, or head tail, and head head. I think these are the 3 cases that would be helpful to control the information. For example, right? What would this case be? And the conditional telltale. Oh, at least 2 heads and 1 tail. At least 2 heads or 1 tail. Yeah. No, I think so. Let's see, right? I think this should be fine. For example, right? If this one, how about this? Let's look at this first. And the condition head will be what?
2 plus the time to see the first head.
First tail, right?
Oh, sorry, first tail, yeah. That's the
Right.
geometry.
So correct. Right. So that's clear, right? If you have head, then you just have to look for a tail. Correct. What about tail head or head tail?
2 plus the time to see a first head, tilde, right?
Correct. Exactly. Agree. So the logic for these two, are they clear? So what about the last one then?
It's 2 plus the time to see the first 2 heads, but then that's some kind of recursion of its own.
No. So hold on, right? Let's try to see. I think the last one, this one is awkward, right? So we at least notice, right? The word 2 heads here is not about consecutive heads. It's about total. Agree? That's the language here. Correct?
Oh, then you can use a negative binomial, some kind of
Exactly. I think this is
N8
2
tilde
plus
tilde.
a negative binomial 2. Correct. I think so. So yeah, right? Do we agree? This is a language of total number of 2 heads, right? That's the way. Correct? Any question here?
Would it be appropriate to use the notation NH tilde tilde? I don't know.
Well, so first of all, right? Notation is not like a God-given thing.
Okay.
So you can invent your own notation, except, right, for example, it should be suggestive, right? And I am not sure if I follow that 100%. But what is my tilde? My tilde is not to say anything, but my tilde is really about a copy, right? So first of all, my tilde has the meaning of that, correct? So when I say tilde, I just want to say that it's really like NH, which is the first time to the first head. But why do I use a tilde here? Because it doesn't count from 0, but it counts from a different point, right?
Oh,
That's
I
my tilde
understand.
notation, right? So piling the tilde on top, what do we mean?
Okay,
Does that
yeah.
make sense?
That makes sense.
No, right. You can define. You
Actually,
define
no,
this
I
to
don't
be
like
like
that.
that. Yeah. Well, I'll just say straightforwardly called a negative binomial, right? Who cares? Is that okay? And again, we use it here, but really, you could do this. Geometric P. Geometric 1 minus P. Right? So that's in terms of distribution. If you notice, there's different meaning we're trying to articulate here. If we do this, we are articulating on the distribution. Well, when we do the other one, we articulate on the pattern, right? Both of them have virtue and maybe vice, who knows, right? But does that make sense? So again, right, I'm saying this because, right, it's good that you ask these questions. Math, right, or really literally, right, what we're doing here is not just solve the problem, but we want to communicate our ideas and our understanding to another person. So however you choose that, right, there's not a fixed way, but hopefully your way, right, it's communicative, right, communicable, right? Okay. Any question? All right, I think let us look at this. Oh wait, hold on. This is exactly we just did this, right? So skip that. Skip that. You know what? I think we talked about this, I think. So yeah, let's finish with this, and this will be it, right? This will be the last problem we'll do for this section, for this lecture, and then we'll move on to Markov chain, okay, next week. So this will be the last one we'll do. All right. So I hope we realize that this is really just about the compound, right? It's really just applying that formula. Right? So you can just really apply the formula. I mean, if you memorize it correctly. Right? So variance times expectation plus expectation square times the variance, right? So variance of xi is, it must be over 12. Hold on. Variance of a uniform, is it a minus b squared over 12, I think. Times 10 plus expectation squared is the variance, right? Plus expectation squared, which is 50 squared, right? Times 10. All right. Do I remember the uniform variance correctly? If you have a uniform AB, then variance of x is b minus a squared over 12, right? Or is it b minus a over 12? I can't remember that. Which one? Is it square without square? How do I know? Anyone remember this? Is it squared or without square?
I'm pretty sure it's squared. It's what you said.
Right, okay, good. Yeah, so sorry, I'm having a senile moment, but all right. Any question?
Where did the 12 come from?
Oh, good question, but no answer there. It's just really about expectation of the square minus the square of expectation. So you integrate a to b x square, 1 over b minus a dx, and then minus, you know, b plus a over 2 squared, and somehow the over 12 shows up.
Oh, so it's part of the formula.
Yeah, the 12 has no super intuitive meaning. It's really just about when you combine the fraction, right, of this and that, you really get the over 12. Yeah. Okay, good. Okay, so this would kind of close the prep, right, materials, and then next week, right, we'll start Markov chain. Okay, so Friday exam, right? Please make sure you have everything ready. And yep, see you on Monday or Friday.
Thank you so much, Professor. Have a nice day.
Have a nice day.
You too.
You.
Yeah. Yeah.
Professor, do you mind staying on for a second?
Go for it. What's up?
I just wanted to talk about the extra time issue.
1 second. If that's the case, let's see if we can stop recording here. Extra time for you, right? Or whatever? Or what? What are we talking about?
Which is that I have a 50%.
Oh, 1 second then. Yeah, that's something we don't want to have on the recording.
It's okay, yeah.
Let's see if I can stop recording. Where do I stop recording? How do I stop recording? More.
It might be on your top right.
Pause, stop recording, stop recording.